Okay, so we're going to start talking about trees. All right, so this is a special kind of graph. In particular, we're going to use them to do certain tasks. Sometimes we analyze a tree by itself, and sometimes we have a graph, and then we use a tree that's a subgraph of that graph to analyze that graph. Okay, so keep both kind of frames in mind and reference. All right, so let's start with the definition. A graph T is a tree if T is connected, because I have to say simple, and contains no circuits. Okay, now I specifically am saying no circuits. The term cycle allows a lot more flexibility. I use the word cycle in its most general form, right? A cycle could involve a lot of backtracking and going back and forth, but a circuit does not allow that. Okay, a circuit requires something like this. Okay, so that's the structural makeup of a circuit. A tree contains none of these. All right. There is a nice little theorem here that is another way of characterizing trees. I'm not going to state it in that format, but let U and V be vertices in a tree. T. Then I could just say there, but I'm saying then there is a unique simple path. Again, another word for this is trail. Between U and V. You can strengthen this just a little bit, which is what I was alluding to before I wrote it down. You can strengthen this and say graph T is a tree if and only if this is the case for every pair of vertices, right? So it's like a unique path graph where you have to be a little bit specific though. I don't want to just say unique path because just like the word cycle, for me the word path is fairly flexible and could involve like going up, over, back, over, up, down, over, and getting there. Right, and so that I don't really want to allow that, so that's why I use the word either simple path or you can use the word trail. Both are perfectly good. Okay, simple just means no, you don't reuse any edges. All right. Okay, so trees are quite common, especially when it comes to data structures. Now, however, this course isn't meant to like build data structures themselves, but the purpose is to analyze trees as mathematical structures. So you want to be kind of careful to not get too deep into using language that is specific to that discipline. Be sure you're comfortable with the language that we're using here. It's often a mistake I usually see is sometimes the students revert to stuff they know because they know some things, then it's unclear what they mean. Okay, so the next thing I want to state a couple little theorems here, two little theorems, and we'll prove them on the next video. So the first one is every tree is planar. Okay, very, very short theorem, 4 words. And then there's another theorem or a corollary to this theorem, and that is if T has n vertices, then T has n minus 1 edges. Okay. You can prove this corollary independently of knowing that every tree is planar, but it's much easier to use planarity as a way to get hold of this. Okay, so the next one, what we're going to do is prove these two. It's not super complicated, and then we'll start working on some things we can do with trees. All right, see you in the next one.